continuous integration with continuous integration servers, and of course continuous delivery came out when that book arrived in 2010. And as I mentioned, it really is just updated engineering practices for software development. So that's the definition of continuous delivery. Now, what that means is that engineering practices that I talk about here apply equally almost for continuous delivery and continuous deployment projects, which is nice because you don't have to have a completely different set. It really is a business decision as to exactly how far do we go down this automation path. So now that begs the question, well, okay, if we understand what continuous delivery is, it's really a set of really efficient, automated engineering practices for software projects. That's really what continuous delivery is. It's a nice, continuous delivery is a nice encapsulation of that principle on software projects. So now, what characteristics of your architecture make it easier to do that is our next question that we want to tackle here. MS has got a great point here. And one of the great challenges when you have super dynamic data is, and test data is always a challenge because it's bulky, et cetera. So it's one of the great challenges that we're still dealing with on Agile engineering projects. So absolutely, particularly for more and more dynamic data. There's a really interesting approach, if you haven't seen it in MS, it's worth mentioning here, particularly if you have really dynamic data that changes a lot. There's a practice being done in the closure community called generative testing, where what they are doing is instead of running unit tests and doing assertions, they are running hundreds of thousands of tests using all sorts of different inputs and then doing statistical analysis over the outcome of those things. So it's an alternate way, and then you query the output of the test run to see if any boundary conditions triggered anything, and so that's actually quite nice if you have very dynamic data. Because you're not making assertions about things, you're actually generating huge amounts of data and then statistically testing to see did any boundary conditions trip anything. So that's generative testing. So let's talk about Agile architecture, and because that's really the essence here is what we want is an Agile architecture that allows us to do continuous delivery. But here's the problem with agility as an architectural characteristic. One of the points that we make in our Fundamentals of Software Architecture book is that architecture characteristics really should be objectively measurable. And what is the objective measure of agility? Well, there is no objective measure for agility because agility is really describing a whole bunch of interrelated things on a software project. This is what we refer to as a composite architectural characteristic because it is composed of a bunch of other measurable things. So that's one of the things that we encourage people to do in our fundamentals book is take composites like reliability and decompose them into things that are actually measurable, like availability is measurable. And it's an aspect of reliability. Same for agility. If we broke this down, what are things that are actually measurable? So deployability is measurable. How often do we deploy things? How often do we get errors during deployments, et cetera? Testability is also something that's objectively verifiable. But really what they're getting at here is modularity and controlled coupling. That's really what they're asking for when they're asking for an Agile architecture. Because think about the goals of Agile software development broadly and continuous delivery specifically. I want the ability to make one small change in my code and then verify that that hasn't broken any other thing within my code base. Well, if I've got really good modular code with good encapsulation, then when I make a change, I just need to check the things immediately around it. Whereas if I have a big ball of mud every change may have a rippling side effect somewhere else. I have to test the entire system. And so having good modularity, well-defined coupling really facilitates this ability to do things like continuous deployment or continuous delivery. So let's talk about a few ways to measure and describe some of these coupling things that are quite useful here, and some actual metrics that are useful to us as architects, and some terminology as well. So this is probably one that you're familiar with, cyclomatic complexity, which works for pretty much any structured programming language. This is a metric that Thomas McCabe created back in the early days of structured programming. The formula is edges minus nodes plus 2, where edges are possible pathways through code and nodes are the actual lines themselves. So if you look at this little decision statement we have over here on the left, if you sketch out its edges and nodes view, what you'll see is 8 minus 7 plus 2, so the cyclomatic complexity of this is 3. What this allows you to do is look at and measure the complexity of methods or functions within your code base, which is often a good indicator of several other things that we'll talk about in just a second. But really complex code is generally not good. But you all know that. There's, of course, a shortcoming with this metric in that it doesn't and cannot distinguish between essential versus accidental complexity. Some problems are just really difficult, and some are made accidentally more difficult. And so it cannot distinguish between those things. But in general, even if you have a very complex problem space, having overly complex code is not beneficial. For reasons we'll talk about in just a second. There are some other metrics that you can use to evaluate code bases. There's a whole family of these called the Chittimer and Kimmerer object-oriented metric suite that look at things like depth of inheritance tree. Weighted methods per class is the cyclomatic complexity summed for all the methods of a class, since all of these metrics are class level. Afferent and efferent coupling is incoming and outgoing coupling, which we'll talk more about in just a second here. There's a really nice metric in the Chittimer and Kimmerer metric suite called lack of cohesion in methods. And I highlight this one because it has such a terrible description on Wikipedia as to what this thing actually does. In fact, it sounds almost like a Zen riddle. The LCOM is the count of the number of method pairs whose similarity is 0 minus the count of method pairs whose similarity is not 0. Huh? This is actually a slightly better definition. The sum of sets of methods not shared via sharing fields, which also sounds a little bit like a Zen riddle. So what is this trying to tell us, this lack of cohesion metric? So consider a component or class where the M's here are methods and the V's are private fields. A is a very cohesive code base because a lot of the methods use all the private fields, whereas B is a very non-cohesive code base because notice that each method just uses one of those fields. B could easily be split up into 3 separate classes or 3 separate components and not hurt anything. And of course, C has mixed cohesion. And so that's really what this is measuring, is given the opportunity for coupling, are you taking advantage of that, or is it just incidentally kind of lumped together? This is a really useful metric if you're doing something like an architectural restructuring or migration, because one of the things you're always interested in is how cohesive is this thing that a whole bunch of other classes are pointing to, and how easily can I break it apart. So this is an indicator. A high score here indicates that it's easier to break a component or class apart than a low score indicates. A lot of what we deal with architects, of course, are components, which are encapsulations of classes, well-defined sets of operations, represented in most of our ecosystems as either packages or namespaces. Components can be containers for classes. They can also show up as subsystems or layers or services or event processors. Microservices may have components inside them, but microservices may be small enough that we don't even need the extra gathering of components inside them, so it could just be a small set of classes. One of the things that we care about components, one of the things we can objectively measure is how the coupling characteristics of components, including two well-known metrics here: afferent coupling, which is the number of incoming connections to a particular component, and efferent coupling, which is the outgoing connections. These are terrible names, but they were named after graph theory when these were defined way back in the 1980s. And so we're kind of stuck with afferent and efferent coupling because all the tools still refer to these as afferent and efferent coupling. Afferent is incoming, efferent is outgoing. And there are a couple of metrics tools that I'll show you in just a second that let you measure coupling. But I want to talk about something else for just a second, which is connaissance. This is from a pretty interesting book called What Every Programmer Should Know About Object-Oriented Design by Miller Page Jones. This was written back in the early 1990s. In fact, 1993 is when I'm wanting to say this book was published. Most of this book is not of very much interest in the current day because he is describing an object-oriented design methodology that basically nobody adopted when he proposed it back in the 90s. But the other cool thing he did in this book is define this term connaissance that I want to spend a couple of minutes here talking about. Connaissance is really a language for describing coupling. So this is not an actual metrics tool that you run on your code. It's a way of describing how things are coupled together. So you may be familiar with, I'm not exactly sure this is, that may be the Star Trek character, not the name of the scientist. There's a famous thing called the Sapir-Whorf hypothesis that is basically that the words that you have for something helps your understanding of that thing. And the premise is that, so for example, people who live in really extreme northern climates tend to have more words for snow than people who live in climates that don't see much snow. I live in Atlanta, Georgia, and so we only have one word for snow there. But in the far northern parts, those languages have a dozen different words for snow, one for snow in the air, one for snow on the ground. So you could argue that they understand snow much more deeply than people from the South. That's basically the Sapir-Whorf hypothesis, that language helps you refine understanding of things. And that's exactly what connaissance is useful for. It's a language that helps describe coupling and ways to make it work better. I don't think it's French, to CJ's point. There's a description in the book about where connaissance comes from. There is a term of where connaissance means connection or coupling or something. So it may be French, but there's an origin to this thing that he came up with. Here's his definition, which is actually the definition that we use for coupling in software architecture hard parts. Two components are connaissant if a change in one would require the other to be modified in order to maintain the overall correctness of the system. So this is basically just coupling. But what he does here is define these different levels of connaissance. From name all the way down to identity, and he further subdivides these into static versus dynamic connaissance. So I won't go through all of these. It's worth going to the website connaissance.io and learn about these terms because here's a good example of why this is useful. So let's say that you were doing a code review as an architect and you ran across some code that looked like this. How would you make this code better? How would you fix this code? And it doesn't have to be anything elaborate. There's actually a menu item in your IDE that would allow you to improve this code. What I'm complaining about, of course, here is this magic string embedded inside this method here somewhere. So how would you improve this? How would you make this code a lot better? Well, at least a couple of ways. The easiest way would be to extract it as a constant and stop referring to this magic string in code, or pass it as a parameter, for example. What we're really doing here is moving it from connaissance of meaning to connaissance of name. So meaning means that I have this magic string embedded there. If I make it a named constant or make it a parameter, I'm moving it up to connaissance of name, which is the most desirable kind of coupling. And so the green to red is pertinent here. Red is the worst kind of coupling you can have up to the best kind. And in general, you want to refactor up and to the left. So this is good advice. So when you encounter some awful code like this on your project, you don't have to do this long description of why you shouldn't have magic strings, etc. It's really just connaissance of meaning, and you want to improve that by refactoring it up to connaissance of name. So that's the idea of connaissance. It's a way of describing this kind of coupling stuff. The other interesting thing about connaissance was he made an observation that's really pertinent around locality. And this is actually directly a quote from the book. A proximal code in the same module, class, or function should have more and higher forms of connaissance than less proximal code. So what he's saying is, the tighter the scope, it's okay to have a more coupling. But the more the scope grows, the less coupling is desirable. And that is exactly, basically, the same message that domain-driven design is talking about. Because the idea of a bounded context in domain-driven design is don't let implementation details leak out of that bounded context. Well, those implementation details is the most intense form of coupling. That's exactly what he's saying here. He just said it in a slightly different way that wasn't quite as catchy as Eric Evans in domain-driven design. But it's basically the same bit of advice here as in domain-driven design. Okay, so we talked about our friends effort coupling. There are tools that let you measure this, which is useful in its own right. But I want to talk briefly about a couple of derived metrics. And then we will, actually, before we get into this, we should go ahead and take our first break. We're already an hour in, and I don't want to go too long before we take our first break. So let's go ahead and take our first break. I'm going to talk about a couple of the Uncle Bob metrics here, abstractness, instability, and distance to the main sequence, and describe those. And then we'll wrap up this metrics discussion and then move into the real merger of architecture and continuous delivery, this idea of wiring architectural checks into your continuous delivery pipeline. So, but let's go ahead and take uses